You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're going to be checking in with some leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on electronic component and design topics, and they're going to include energy harvesting, wireless power transfer, EMI issues, and so much more. In fact, today's episode, we are discussing a rather triggering topic for a few designers, specifically circuit designers, and that topic is safety standard compliance. Now, with several different international standard bodies like UL, IEC, CCC, the list goes on, there are dozens of possible applicable standards, and some of these are hundreds of pages long. So how is a designer such as yourself supposed to ensure their circuit meets the applicable standards? And for that matter, how does one even determine what standards need to apply? Now, this uncertainty, combined with the specter of a costly project delay due in the 11th hour rejection by a testing house, well, this can all lead to a couple potentially very costly mistakes. In an information vacuum, some of these designers sometimes decide to take a better safe than sorry philosophy, and they over-design their circuit and they over-specify their components. And then others take the opposite approach. They wait until they have a working design before doing any sort of safety retrofit. So what does it take to meet safety? First, let's take a look at what's needed to meet the typical safety standard requirements. Now, the primary purpose of safety standards for electronic equipment is the obvious. It prevents a hazardous or non-intended mode of operation from injuring the user. And for this discussion, we're going to limit our consideration to preventing electric shock hazards. There are two main tools that you can use to actually mitigate shock hazard. The first is using a combination of electrical insulation and distance to put a dielectric barrier between the shock hazard and the user. The second one is the use of galvanic isolation, and this is where the input and the output are connected through a magnetic field in a transformer rather than a direct electrical connection. Now, in many of our modern day power supplies, the use of a transformer is actually used, and it supplies galvanic isolation. Now, this is effective, and most safety standards require the additional use of electrical insulation and safety distances, but typically, they're built into the transformer itself. And while transformers provide galvanic isolation, there are three common levels of insulation that you also have to be aware of. First is the functional insulation, and this is only what is required for the part to function electrically, and there's no extra insulation provided for safety. The next is basic insulation. This adds one extra insulation barrier for safety. And the final one is reinforced. This adds two extra independent insulation barriers for safety. In addition to the insulation, you need to consider the working voltage of the circuit, as the safety distance requirements and insulation thicknesses directly correlate to working voltage. Generally speaking, the working voltage is considered to be the sum of the highest input and output voltage that the circuit will see under normal operation. So let's illustrate over-designing safety with the use of an example. Let's say that you're using a 20-watt flyback topology for your application. Now, you know that you need to comply with safety standard IEC 62368-1, and that reinforced insulation will be needed with a 250 root mean square voltage, or VRMS, working voltage. However, you're unsure if they need overvoltage category 3, which is for equipment intended to form part of a building wiring installation, or overvoltage category 4, and this is for equipment installed at or near the origin of the electrical supply to a building. Now, while it might be tempting to bypass all this confusion and just design for that category 4, what is this cost? Now, a look at the creepage and clearance tables in IEC 62368-1. This shows that the safety distances go from 5.5 millimeters to 8 millimeters as we move from category 3 to category 4. On a 20-watt part, That is only 21 by 25 millimeters. That's a non-trivial increase. The obvious consequence is to increase the PCB area required for the part from 525 millimeters squared to 578 millimeters squared. That's a 21% increase, and that is not something most designers would find very desirable. Now, maybe the increase in PCB space is okay for your application, but what are the other costs? Well, as it turns out, there are many commercially available transformer bobbins that meet the 5.5 millimeter safety distance requirements, but there are very few options that can meet that 8 millimeter requirement. Likely, this means that a custom bobbin will need to be tooled up, which is going to cost several $1,000s and add up to 12 weeks to the initial lead time. Additionally, unless the volume exceeds 100,000, the piece price will likely be higher due to the custom bobbin, and this can increase by as much as 20%. Now, let's suppose that instead of making the part larger, we simply tried to design the best transformer in the same price. This may not be possible, but even if it is, it's still going to require using more of the bobbin's finite winding space on insulation materials. Think margin tape, thicker wire coatings, etc., and then less on copper. This is going to lead to a measurable reduction in efficiency and increase in heating of the transformer. Another common mistake made by most designers who are unfamiliar with the necessary safety standard, this is to wait until the very last minute in the design process to apply the safety requirements. Now, as troublesome as it is to overestimate the safety requirements early on in this design process, the effects of ignoring safety requirements until the very end can be devastating. Now, this whole kick in the can thinking goes like this. Let's not let safety delay our design, so we're going to start with the initial design while we evaluate the safety requirements. For a while, everything appears to be going well. Functional insulation magnetics are obtained, the PCB is all laid out, the testing is done, efficiency and performance look great. Everyone is feeling pretty confident. Then the magnetics vendor is informed, oh, by the way, we need to meet these 3 safety standards and also have reinforced insulation. And designing to meet safety standards requires the careful evaluation of several trade-offs. It's much easier to account for these trade-offs before the PCB has been all laid out and the component real estate has been allocated. If safety is not considered upfront, likely the only workable solution will be to grow the transformer size, and this results in a partial or even complete redesign of the PCB. So how is this going to affect other aspects of your design, like the enclosure? Does your cost, likely already reported to management and agreed upon with the customer, do they have room to grow at this late stage in the design? Customers are very often dismayed to learn that the size of the magnetics has to grow by 50% and the efficiency will be reduced. But why? Why does safety affect efficiency? On the surface, the two may not seem very related, but on a deeper level, this is showing some critical connections between safety compliance and efficiency. First, let's take a look at the factors that affect transformer efficiency. The first is good coupling between the windings, reducing leakage inductance. Next is maximizing the use of copper. This is to reduce DC resistance losses. And finally, using stranding and Litz wire to reduce AC losses. So let's take a look at the effect of meeting a reinforced insulation safety standard on these terms. Now, in order to meet safety requirements, it's necessary to use wire with more layers of insulation and to use margin tape. This helps to increase the creepage and clearance distances. These remediations cause an increase in space between the various windings and between the individual turns. This will in turn lead to reduced coupling and increased leakage inductance. Additionally, every cubic millimeter of the winding window devoted to insulation materials is 1 less cubic millimeter that can be used for copper, further reducing the efficiency. Lastly, the requirement to use triple insulated wire greatly reduces the available Litz wire types, and this makes it difficult to optimize the magnetics for AC losses. Now, from this, we can see that almost every design change required to a transformer to meet safety can also have a negative impact on safety. So what else is there to be done? Are we stuck? Well, not exactly. Some of these safety-induced losses can be clawed back by simply using a larger package for your magnetics. Using a larger package has some advantages, such as increase in winding window volume. This allows for more copper. Increased distances between windings and terminations, possibly allowing for the reduction of elimination of margin tape, therefore increasing coupling, and a larger core area for reduced core losses and possibly fewer winding turns. Of course, increasing the package size comes at the expense of PCB real estate and the part cost, and it may be necessary depending on the efficiency requirements of your application. Careful consideration of these trade-offs is required, and this is a good topic to discuss with your magnetic supplier early on in the design process. So now that we have covered some of the pitfalls associated with failing to fully understand your safety requirements, what can you do? How can you possibly be expected to understand over 300 pages of safety standards, let alone several of those safety standards? Well, fortunately, there is help available. One route is to use a safety standards consultant. Now, these individuals or even companies devote their time and energy to not only comprehending the standards, but also knowing their real-world application and what to expect when the product is submitted for evaluation. Quite often, you can find one that specializes in your industry. Another option, which can be equally effective but is far less costly, is to rely on your magnetics vendor to assist you with this process. Designers of custom magnetics parts have to have a very intimate understanding of several key safety standards, and they can help you to make sure that you're meeting the standards appropriately. Choosing the right magnetic supplier can add more value to your design than just supplying reliable components. In conclusion, understanding safety requirements is both a technical as well as a strategic necessity for circuit designers. While safety compliance can seem overwhelming due to the vast number of standards and the technical complexities they introduce, the risks of ignoring or even misinterpreting these requirements can often lead to substantial project delays, redesigns, and budget overruns. The temptation to either overdesign as a safety approach or to delay safety considerations can ultimately drive up costs in unexpected ways, either from increased material expenses to larger component footprints, reduced efficiency, and even custom part requirements. The most effective approach combines early planning with expert guidance, either through safety consultants or experienced magnetic vendors, to navigate the standards with precision. This investment not only ensures regulatory compliance, but also optimizes the design for both functionality and cost-effectiveness, leading to a safer, more reliable product and a smoother development process. For all your safety questions and transformer design requirements, we encourage you to follow up with your Worth Electronic magnetics experts. Find a consultant near you or chat with our online experts at www.we-online.com. While there, you can also browse our selection of custom magnetic solutions, as well as the off-the-shelf power magnetics, such as inductors, PFC chokes, wireless power transmission, gate drive transformers, and so much more available at Worth Electronic online. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.